Hello and welcome to the next edition of the BriefingsDirect Voice of the Customer podcast series. I'm Dana Gardner, Principal Analyst at Inter Arbor Solutions, your host and moderator for this ongoing discussion on high-performance computing trends and innovations. Our next discussion explores a program to expand the variety of CPUs that support supercomputer and artificial intelligence intensive workloads. We'll now learn how the Catalyst program in the UK is seeding the advancement of the ARM CPU architecture for HPC, as well as to establish a vibrant software ecosystem around it. Stay with us now as we hear about unlocking new choices and innovation for the next generations of supercomputing. With that, please join me in welcoming our guest. We're here with Dr. Englim Goh. He's Vice President and Chief Technology Officer for High Performance Computing and Artificial Intelligence at Hewlett Packard Enterprise. Welcome, Dr. Goh.
Hi, Dana. Thank you.
We're also here with Professor Mark Parsons, Director of the Edinburgh Parallel Computing Center at the University of Edinburgh. Welcome, Professor Parsons.
Hi, Dana. And please just call me Mark throughout this.
All right. Mark, why is there a need now for more variety of choice for CPU architectures for such use cases as high-performance computing, artificial intelligence, and supercomputing?
Do you know, in some ways, this discussion is a bit odd because we have had huge variety over the years in supercomputing with regard to processors. And it's really only in the last 5 or maybe 8 years that we've ended up with really the majority of supercomputers being built from the x86 architecture. And I think it's always good in supercomputing to be on the leading edge of technology. And I think getting a bit more variety into the whole processor story is really important. And it's interesting not just from the variety point of view, but also the point, can we make different processor designs perform better for AI workloads or supercomputing workloads? You know, what is the best type of processor for the sort of processing we want to do today?
And so what is the Catalyst program? Why did it come about? And how does it help address those issues?
So the Catalyst UK program is a program that's jointly funded by a number of large companies. But it involves about 4 companies, but it also involves 3 universities as well in the UK. So the University of Bristol, the University of Leicester, and my own university, the University of Edinburgh. And the idea is, and I think this is particularly got a UK focus because, of course, ARM is a company that's based in the UK. With a long history in the UK of exploring new processor technologies. And what Catalyst has done is each of the 3 universities are hosting a 4,000 core ARM processor-based system. We're running them as services. So in my university now, we've got a number of my staff using the system, but we've also got external academics using it, and we're gradually opening up to other users. And we want to get as many people as possible understanding how difficult it's going to be for them to port their codes onto ARM, or rather, as we'll probably explore in this podcast, how easy it is, but also at the same time breaking stuff, right? You only learn by breaking stuff, and I think we're going to have to understand which bits of the software tool chain, for example, need some work, because predominantly ARM is sat in the mobile phone world up until now, and the supercomputing and AI world is a different space for the processor to be operating.
And Dr. Goh, why is this program of interest to HPE, and how do you think it will help create new opportunity and new performance benchmarks for such uses as AI?
Yes, Mark, please call me England. And Mark makes a number of very strong points related to this. Right? First and foremost, we are very keen as a company, right, to broaden the reach of high-performance computing amongst our customers. And if you look at our customer base, a large portion of them actually come from the commercial HPC side, the retailers, the banks, for example, the financial industry. So letting them have this reach towards high-performance computing is important. As such, a variety of offerings makes it easier for them. So that's the first thing. The second thing is this recent re-emergence of application in artificial intelligence also broadens the user base. And then there is also a need, later you'll see in our discussion, right? There's a need for specialization in certain areas of processor capability. And we believe, in this case, the ARM processor, given the fact that it enables different companies to build innovative variations of the processor, will then provide a richer set of options for this new upcoming and re-emerging application area in artificial intelligence.
And what is it specifically, Mark, about the ARM architecture and specifically the Marvel Thunder X2 ARM processor that is attractive for these types of workloads? Why is this an interesting avenue in the direction of the speeds and feeds angle?
So I think it's absolutely the case that all numerical computing, and you can put AI in there, you can put supercomputing in there, you can put desktop technical computing in there, is driven or controlled rather by memory bandwidth. And this is just getting data to the processor so the processor core can act on it. And what we see in Thunder X2, and I think we'll see in future iterations of this processor, is really, really strong memory bandwidth. And what people don't realize a lot of the time today is that a vast amount of time, processor cores are just waiting for data. And the faster you can get the data to the processor, the more compute you're going to get out of that processor. And that's one particular area that the ARM architecture is very strong in.
Yeah, indeed. Memory bandwidth, as Mark mentioned, is the key, and especially not in supercomputing applications, and also especially in machine learning, where the training phase, where the machine is in the early phases of learning, before it does prediction and inference, it has to go through the process of learning. And this learning is a highly data-intensive process where you have to consume massive amounts of historical data and examples in order to tune itself into a model that can make good predictions. So memory bandwidth is the utmost in the training phase of machine learning. And related to this is the fact that the ARM processor, its core, right? The processor's core intellectual property is available to many companies to innovate around. And companies, therefore, recognizing this need, could then apply that intellectual property and then have high memory bandwidth innovations around it and come up with a new processor. And as such, the ability to allow different companies to innovate is valuable. And we see one outcome of it right now in this processor.
And Eng Lim, it seems that this really fits in well with the larger Hewlett Packard Enterprise drive towards memory-intensive computing, not just at the CPU level, but across the architecture for the entire the computer, the server, and even the data center. So perhaps you could address why the massive amount of memory, the value that you get with the ARM processor fits into a larger HPE strategy.
No, absolutely. And the ARM processor, together with the other processors, it's important to provide these choices and options for this strategy of Hewlett Packard Enterprise, right? That is, number one, edge-centric. And then number two, cloud-enabled, which is the data center side you mentioned. And then finally, data-driven. So you can see from these three parts of that strategy where the commonality there is moving data within each of these sectors and across those sectors, right? As such, the ARM processor allowing different companies to come in to innovate and producing processors that meet the needs of these various kinds of sectors, we see as highly valuable and supports our strategy.
Mark, ARM Holdings controls the intellectual property, but there is this ecosystem both on the processor design as well as the software that can take advantage of it. Tell us a little bit about that ecosystem, why it takes a team or a sport approach, and how the Catalyst UK program is facilitating more of a vibrant ecosystem.
Yeah, I think the whole ARM story is a very, very interesting story. This company that grew out of really home computing, in fact, 30, 40 years ago now. And the interesting thing is the way that they're an intellectual property company at the end of the day. The ARM itself doesn't make processors. It designs processors and sells those designs to other people to make them. So we've got this wonderful ecosystem of different companies making their own ARM processors or making them for other people. There's a wide variety of different ARM processors inside mobile phones. It's no surprise that it's the most common processor in the world today. People think that x86 processors rule the roost, but actually they don't. The most common processor you'll find in anything is an ARM processor. And as a result, there's a whole load of development tools that come both from ARM, but also the developer community that support people wanting to develop code for the processor. And I do think that in the context of Catalyst is interesting because talking to ARM, it's quite clear that many of their tools are designed to meet their predominant market today, which has always been the mobile phone market. And as they move into this space of much higher end computing, it's clear that, we may find things in the program where the compiler isn't optimizing some bit of the code particularly well, where certain libraries are difficult to compile and things like this. And I think this is what interests me and excites me about the whole Catalyst program, where we're getting to play with leading edge technology and show that it is easy to use, whilst also finding out interesting stuff about it.
And while the CPU is being more purpose-focused for these high-intensive workloads, we're seeing more applications being brought in as well. So that porting process that you alluded to, what is the process around porting apps from x86 to ARM, and how easy or difficult is it, and how does that fit into the Catalyst UK program?
So all three of the universities are porting various applications that they commonly use. But EPC is taking a particular approach. We run the National High Performance Computing Service for the UK called Archer. And as part of that, we've run national services since 1994. But as part of the Archer service, we decided for the first time to offer many of the common scientific applications as modules. You just ask for the module that you want and you use it. Because what we saw were users were compiling their own copy of chemistry code, for example. And we had multiple copies of these codes, some of them identically compiled, others not compiled particularly well. So we've got into a model of offering about 40 codes on Archer as pre-compiled, where we try and keep them up to date and patch them, etc., etc. And what we're doing with Catalyst is, the way we did, I've got 100 staff at EPCC, and staff take a code that they look after. So I've asked all those staff to get an account on the Catalyst system, take their code across, and spend an afternoon trying to compile it. And some of them, we already know they just compile and they just run. Others, there may be some problems with make files or whatever, or even a problem with the compiler. And it's those that we're passing on to ARM and HP and saying, look, this is what we found out. The important thing we found so far is actually there are very few programs. Most codes are simply recompiling very, very smoothly.
And how are the HPE systems a part of this compiling activity and the whole porting strategy? How does HP support that, both in terms of its corporate support, but also with these systems themselves?
We are very keen about the work that Mark and the Catalyst program are putting effort into. The reason is because, as Mark mentioned, origins of the ARM processor came more from the edge side of our strategy, or the edge-centric side of our strategy, and in mobile phones, for example. And we're very keen to see how this program, together with the systems we have shipped to the DOE that was announced at the Sandia National Lab, a large ARM processor-based supercomputer called Astra, all these efforts going on in the area of HPC application. We're very keen to see how this processor works and the compilers for it work with HPC applications. So this is the key to our high interest in these different efforts in the UK and also in the US.
And as we look to the larger addressable market here, with the edge, with artificial intelligence being very high growth markets, a lot of excitement about the potential here, it strikes me that while we still call it supercomputing, that something that's been around for 30 or 40 years is really not fully mature, that we're still looking at a whole new era of innovation. So Mark, do you see supercomputing as in its heyday, sunset years, or perhaps even in its infancy?
I absolutely think that supercomputing is still in its infancy. There are so many bits of the world around us that we've never even considered trying to model or simulate or understand on supercomputers. I think it's strange because quite often people think that supercomputing has solved everything, and it really, really hasn't. And I'll give you a direct example of that. A few years ago, in a European project I was running, and this is about 2013-14, the project won an award for simulating in the highest accuracy water flowing through a piece of porous rock. And it took over a day on the whole of the national service, and we won a prize for this. And we only simulated 1 cubic centimeter of rock, okay? People think supercomputers can solve massive problems, and they can, but the universe, the world, is a complex place. And really, we've only scratched the surface of modeling and simulation. And do you know what's really driving, at the moment, this interesting moment in time with AI and supercomputing, and I would also argue a lot of data analytics, is for the first time, we've got at our fingertips very, very large amounts of data, very rich data from multiple sources. And supercomputers are getting much better at handling these large data sources. And I think the whole AI story, I think the reason it's really hot now and lots of people involved in it is not actually about AI itself. It's in our ability to move data around and use that data to train these AI algorithms. And I think the link directly into supercomputing is because, in particular in our world, we're good at moving large amounts of data around and always have been. And so I think part of the whole synergy between supercomputing and AI really is not to do with supercomputing or AI. It's to do with data.
Eng Lim at HPE, how do you see the evolution of supercomputing, and do you agree with Mark that we are only scratching the surface?
Yeah, absolutely. Very, 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 very early scratch, in fact. It's still very early. I'll give you an example. Solving games is important. For example, to develop a method of strategy for cyber defense, for example. Now, if you just take the game, the most recent game that machines have beaten the best human players, the game of Go, much more complex than chess in the number of combinations. The number of combinations is actually 10 to the power 171. If you comprehensively went through all the different combinations of that game, 10 to the power 171. You know how big that number is? Well, okay, if we took all computers in the world together, all the supercomputers, all the computers in the data centers of the internet companies, and put them all together, run them for 100 years, and all you can do is 10 to the power of 30, far from 10 to the power 171. So you can see, just by this one game example alone, we are very early in that scratch, right? So that's the first example. The first class of example. The second group of examples is related to this new way supercomputers are being used now. So with machine learning towards artificial intelligence, there is now a new class of applications that's entering, as Mark mentioned, that's entering into the fray of how supercomputers could be used. So traditionally, most of the supercomputers have been used for simulation. That's what I call top-down modeling. You create your model out of physics, and then you run your supercomputer with that model to try and make a prediction. In the new way, in a new set of way of prediction, using the machine learning approach, you do not start with physics. You start actually with a blank model, and then you keep feeding data, the outcomes of the past, history, examples. Keep feeding data into the model that is written in a way that each new piece of data is fed and a prediction made. And if the accuracy is not high, you keep tuning the model, and then with thousands, hundreds of thousands, millions of examples, the models get tuned to a pretty good place to make a prediction. So I call that the bottom-up approach. So now you see people applying both approaches. Supercomputers traditionally used for simulation top-down, and now people are also employing the bottom-up machine learning approach to work in tandem to make better and faster predictions. So now supercomputers are now being employed into a new class of application now in combination with the traditional, albeit still the gold standard, simulation.
And Mark, it sounds like we're really talking about the democratization of supercomputing. We're able to do more at the core level. We're able to bring more data in. We're able to get to that data and use it in new ways, and therefore extend the applications and uses. But one of the other limiting factors has been cost and price and value. What is it about what's happening now that is decreasing the cost, increasing the value, and therefore opening these systems up to more types of uses and more problem solving?
So I think it's absolutely clear that cloud computing is having a big impact, just on everything that we do, to be quite honest. I mean, we've all got our pictures in the cloud, we've got our music in the cloud, etc. In fact, HPC last year got rid of its file server. All our data is in the cloud for running the actual organization. I think the cloud is great in as much as it allows people who don't want to operate and run a large system 100% of the time to access these technologies in ways they've never been able to do before. I think on the other side of that is that there are fantastic software frameworks now that didn't exist even 5 years ago for doing AI. There's so much open source software for doing simulations, etc., etc. Now, it doesn't mean that an organization like EPCC, which is a supercomputing center, are going to stop hosting large systems. We're still great aggregators of demand, and I think Supercomputing Center will still have the largest computers. But it does mean that for the first time, through the various cloud providers, any company, any small research group in university has access to the right level of resources that they need in a cost-effective way.
Eng Lim, do you have anything more to offer on the value and economics of this, maybe on a demand-paying basis rather than a capital expenditure basis? And also, it strikes me that there are many of these workloads that you simply can't use a cloud for, if for no other reason that you can't get the data in and out in a practical way.
Oh, great question. There are some applications and institutions with processes that work very well with the cloud, and there are some applications that don't, and processes that don't. That's part of the reason why we embrace both. And in fact, we embrace the cloud, and also we build on-prem solutions for our customers, like the one we work also have something that is a mix of the two, and we call that Green Lake, which is the ability for us to acquire the system the customer needs, but the customer pay per use. So these are some of the options we put together, right, to allow this choice to our customer, because there is a variation of needs and processes. Some are more CapEx oriented in the way they acquire capability, and others are more OpEx oriented, for example.
All right. We've talked about this at some length, but it's usually quite powerful when you bring some concrete examples into the discussion. So from either of you, do you have some examples of where some of the fruits of Catalyst and some of the benefits of the ecosystem approach have led to actual applications, use cases, and demonstrated innovation that's something that probably couldn't have been possible before?
So I think for me, I feel this is a very boring answer, Dana, but the truth is that what we're trying to do is show how easy ARM is to use. So we've taken some really powerful, important codes that run every single day on our big national services, and we've simply moved them across, and the users don't really understand or don't need to understand they're running on a different system. It's that boring. We have picked up one or two problems with codes that probably exist in the x86 version, but because you're running a new processor, it exposes it more, and we're fixing that. But in general, and this is absolutely the wrong message, I understand, for a big corporate interview, we're proceeding very boringly. The reason I say that is it's really important that this is boring, because if we don't show this is easy, people won't put ARM on their next procurement. They'll think that it's too difficult, that it's going to be too much trouble to move codes across. So one of the aims of Catalyst, and I'm joking a bit here, one of the aims is definitely to be boring. And I think at this point in time, we are succeeding. More interestingly, though, one of the other aims of Catalyst has been, when you look at the ARM systems that are around in the world today, they tend to still do their storage on x86. So the storage will be running Lustre or GPFS or whatever, sitting on x86 boxes. We've made a decision that we're going to do everything on ARM if we can. And so at the moment, we're doing a big bit of work looking at different storage softwares on ARM servers. So we're looking at Ceph, at Lustre, at BGFS, because I think that unless you've got this sort of part of the ecosystem running on ARM as well, people won't think it's as a pervasive solution as x86 or Power or whatever. So I think that's the particular area where we're doing a lot of innovative work at the moment.
In this case, boring is good. Seamless movement of code across different platforms is the key. It's very important for an ecosystem to be successful. It needs to be easy to develop code for, and it needs to be easy to port to. And also just as important with our commercial HPC side, for our broader HPC customer base. In addition to customers writing their own code and compiling well and easily to ARM, we also would like the ISVs, the independent software vendors that build different codes in engineering, in chemistry, to also be encouraged to come to this new ecosystem. And that is also there's a very important part of making a platform successful.
Yeah, and if I could cut in there, actually, that is one of the key things that we intend to do over the next 6 months. We've got good relationships, as has HPE, with many of these big ISVs and small ones too. And we want to get them, give them an account in the system, let them compile their codes up, give them some help to do it. And I think that's really important, that we end up with a group of the major ISV codes all sitting on ARM, all running successfully.
All right. Well, if we're in a necessary, boring period for getting confidence and buy-in, what will happen when we get to a more exciting stage? Where do you see this potentially going? What are some of the use cases that we'll be addressing using supercomputers, even behind the scenes and invisible? But how will this impact business, commerce, public services, public health?
Well, not necessarily. Well, I put it another way. Not necessarily boring, but brilliantly boring. Well, let's put it that way. Yeah, you will. You see, richer choices encourages more to come to use supercomputing. I think that's the key. Supercomputing and high-performance computing needs to reach a broader customer base. That's the goal of our team within HPE, working on HPC. That's part of the reason why over the years we've been increasing our reach to the commercial HPC side. As I mentioned, the financial industry, the retailers, and so on. And with new opportunity coming in with a bottom-up approach approach of using HPC, that is, instead of building models out of physics, you train the models with example data. This new way of using HPC will reach out to even more users. So success of our supercomputing industry is getting more users with high diversity and more of the users to come on board.
Mark, last word to you. What are some of the exciting outcomes that you anticipate?
So I think as we get more and more experience with ARM, I think that it becomes a serious player in our next procurement. And if you look around the world today, in Japan, for example, they've announced a really big ARM-based supercomputer that's going to be close to the exascale when it's launched. I think if we look around, you've obviously, HPC have sold a very large system to the Sandia National Lab. I think I would predict that in the next 3 or 4 years, we're going to see some very significant supercomputers up at the exascale built from ARM processors. And based on what I see people talking about in terms of the next generations of these processors as manufacturers improve them, I think we're about to enter a really, really exciting time with these processors.
All right, I'm afraid we'll have to leave it there. We've been exploring a program to expand the variety of CPUs that support supercomputer and artificial intelligence intensive workloads. And we've specifically learned how the Catalyst UK program is seeding the advancement of the ARM CPU architecture for HPC, as well as helping to establish a vibrant software ecosystem. So please join me in thanking our guests. We've been here with Dr. Eng-Lim Goh, Vice President and Chief Technology Officer for High Performance Computing and Artificial Intelligence at Hewlett Packard Enterprise. Thank you so much, Eng-Lim.
Thank you, Dana. Great interview.
And we've also been joined by Professor Mark Parsons, Director of the Edinburgh Parallel Computing Center at the University of Edinburgh. Thank you, sir.
Thank you, Don. It's been a pleasure.
And a big thank you as well to our audience for joining us for this BriefingsDirect Voice of the Customer HPC Trends and Innovations discussion. I'm Dana Gardner, Principal Analyst at Inter Arbor Solutions, your host for this ongoing series of Hewlett Packard Enterprise sponsored discussions. Thanks again for listening. Please pass this along to your IT community and do come back next time.